Okay. Actually, I need these two. Hello. We're back. Video 4, related rates. So in order to finish a related rate, you need to use these five rules, not rules, but techniques, alright? So finding the derivative, right? But before we've been using finding the derivative with respect to x. What makes related rates important is we're finding the derivative, but now it's respect with time, right? And by having it with respect to time, it changes everything. So we're also going to use implicit differentiation, finding the derivative on both sides. We're going to use the chain rule, product rule, and quotient rule. These two, you might not have to use it all the time, but you are going to need to know it to be able to advance. So today we're actually going to do 3 problems. And so here I wrote them down, so we won't have to waste so much time. So let's start with the first one. So I'm going to just read it out and then I'll explain to you how to solve it, right? So a pebble is dropped into a calm pond, causing ripples in the form of concentric circles, as shown in figure 1. Here you can see it's just circles, rings going out. The radius r of the outer circle, of the outer ripple, is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? Alright, so first step, always draw your picture, right? Okay, so here for the first step, we're going to draw our concentric circles. And here are our different r values that are changing, right? And then here, okay. Step 1, draw a picture, check. Step 2 is write down your givens, alright? So it tells us that the radius r of the outer ripple is increasing at a constant rate of 1 foot per second. So that means d dt of the radius is 1 foot per second. Okay? And it also tells us when the radius is 4 feet, what is the rate of the total area changing, right? So d dt of area. We're trying to find this. So here, step 2, write down your givens, check. Alright. So now that we have these, now we're actually going to start with the problem, right? So the first thing that you have to do is how to connect, how to relate radius and area of a circle, right? So if we think back to geometry, we know the area of a circle equals pi r squared. So that's our equation, area equals pi r squared. From now here, then, we're going to go on to implicit differentiation. So we're going to find the derivative of both sides. So d dt of the area is equal to d dt of pi r squared. Alright, so here it's good because this is what we're looking for, right? So this is fine. And then now we're going to have to simplify this. So remember, don't forget to write this down. The pi, since pi is actually a number, right? It's a 3.14, blah, 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 blah. So you can actually just take that out. And then we're just finding the derivative of r squared. So now we're going to have to use the chain rule on this, right? So d dt of area equals pi. Remember what you do is you bring the product down, so 2. Your argument, which is inside, always stays the same, and then you find the derivative of your argument, so d dt of r. So now when we have this equation, I always double check to see that everything fits in and I'm not missing anything, and it looks like everything's good. And then now it's just simple. Now all we have to do is just plug what we have up here into our equation. So we're trying to find for, here, let me break this out. So we're trying to find d dt of the area, right? Okay. Pi times 2. It tells us the r is 4 feet, right? So times 4 times, it tells us the rate of r, what's it changing, times 1. Now you just have to multiply it out, so it'll be 8 pi. So derivative, so the area is changing at 8 pi, and remember, you always have to put in your units, so feet per second. And then that's your answer. See, it's very simple. Just follow those rules, and it'll help you get the answer. So now let's move on to the second question, right? Okay, second question. Air is being pumped into a spherical balloon, see figure 2, just a balloon, smallest, bigger, and then biggest, at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. So remember, step 1, draw your picture. Of course, over here they already gave you the picture, right? But you should always just draw it so you can help yourself. So here we have a balloon, and air is being pumped into it, so it gets bigger and bigger, right? And the radius of the balloon is also going to get bigger. Alright, so draw a picture, check. Then now we're going to write our givens, right? So at a rate of 4.5 cubic feet per minute. So it's telling us that, so air is being pumped into it, okay? So air pumped into balloon at 4.5 cubic feet per minute, alright? That's the same thing as volume. Alright, our next given, find the rate of change of the radius. So we want to find the rate of change of radius when the radius is 2 feet. Okay, so now we have our givens. Now we want to relate this. How can we relate volume with radius of a sphere, right? So you know the volume equals 4/3 pi r cubed. Okay? So now that we have this, now we can use the implicit differentiation, right? So wait, give me a second, my bad. Okay, yeah. So remember implicit differentiation. So d dt of volume equals d dt of 4/3 pi r cubed. Again, 4/3 is an actual number, and pi is also a number. So you can just take that out of the derivative, 4/3, because you're eventually just going to have to multiply it, right? So then we have d dt of r cubed. So now you do the chain rule on that. So d dt of volume equals 4/3 pi. So 3 times r, remember your argument never changes, squared, times the derivative of your argument, which is just r. So double check, make sure you have all the components, d dt of volume. Yeah, okay, here's actually it's telling us the d dt of the volume, alright. 4/3 pi, 3, they give us r check, we're trying to find that, perfect. Now all you do is just plug in the numbers, simple, simple, simple. Alright, so we have 4.5 equals 4/3 pi 3 times r squared times d dt of r. That's it. So then you just do 4.5 equals, 3's cancel out. This turns out to be 4 times 4, so it's 16 pi times d dt of r. We do 4.5 divided by 16 pi equals d dt r. And always, don't forget your units. So feet cubed per minute. And that's it. See, it's very simple actually. I think the hardest is finding the equation that it relates. I think that's the hardest thing that you're gonna have to do, right? But if you just remember back to geometry and try to remember all those equations, then actually you'll be fine. Let's move on to the third one. This one's actually kinda hard, but if you think it through, won't be too hard. So 3, an airplane is flying on a flight path that will take it directly over a radar tracking station. The distance s the distance s is decreasing at a rate of 400 miles per hour. When s is equal to 10 miles, what is the speed of the plane? Alright, draw our diagram. Here they gave it to us, right? Sometimes they won't be so generous. So we're just going to draw it out and acting like they just never gave it to us. Because sometimes that'll actually just happen. Alright. So here they tell us it's 6 miles, okay? And distance s, oh wait, no.